Hello everybody, my name is Mr. Basil, and in today's video we're going to be studying topic 6.4, and we're going to be going over at the end some calorimetry examples. I'm calling this daily video number alpha, and in this video you have a few reminders on some terminologies, and I'll explain when to use MC delta T, and again the main focus of this one is going to be some calorimetry work examples. My name is Tucker Basil, and I teach AP Chemistry at Chaska High School in Chaska, Minnesota, and I'm here on behalf of High School Plank. Okay, a few things before we get started with the examples. Remember that enthalpy is pretty much the same thing as energy for all the purpose that we're going to use it in this class. Remember that systems exchange energy via heat or heating, which is also known as particle collisions. It says particle collisions, and that is wonderful. Or particle jiggling. That's another way that another mechanism in which heating takes place. This changes the system's thermal energy, and I say systems as in plural systems. So when something changes its thermal energy, it's changing, well, its temperature. And there are other ways that a system can change its energy, but that is the main way that it will change its thermal energy. We'll study phase energy and chemical or bond energy in the future. Also, remember the word heat is often used ambiguously, even by amazing teachers. When a system changes its thermal energy, that energy is being transferred into or out of its system via heating. The amount of thermal energy change equals the amount of heating that is taking place. So, this equation, Q equals M times C times T. The above equation is used to calculate a change in thermal energy or the amount of energy being transferred via heating. Q is the amount of energy transferred via heating, though most would simply call it the quantity of heat. Sorry for swearing. The other thing about this equation, the AP Daily that exists currently for C, that talks about the units of C, what is the specific heating capacity. You should make sure you watch that one if you're not sure what's going on with that, or what delta T and M and all that other things are. I just wanted to talk about what Q was, because some students, usually students, will express some confusion about Q, like what is Q and so on. A plus or minus for Q tells us the direction of energy transfer. It does not necessarily tell us if the process is endo or exothermic. And again, your perspective matters. So if your perspective is from the system and the Q sign is negative, that means that energy is leaving the surroundings and going into the system. If your perspective is from the system, which it's usually you want it to be, your perspective to be the system. If Q is negative from the system's perspective, that means that energy is leaving the system, which then would mean that the Q for the surroundings should be positive, because the energy would be leaving the system going to the surroundings, and vice versa. Okay, sometimes you're going to see this written as Q equals MC delta T. Sometimes you'll see this is written as ETH, so thermal energy equals MC delta T. And sometimes you'll see it as the change in enthalpy equals MC delta T. You may see all of these things. It's okay. It depends upon the situation. So if you're just looking at a system, you're not dealing with any surroundings or anything, you may just see this as the change in thermal energy, which is fine, because that's basically the same as how much heating is occurring. And then at some point when we start talking about enthalpy and incorporating that with it, remember, a change in enthalpy is the same as the change in it's change in energy, which could be considered a change in thermal energy. And if some amount of energy is changing, it's probably happening via heating. So again, sometimes these are used interchangeably, which can be frustrating, but it's okay, because they all basically mean an amount of energy. Now it is time for some examples. Alright, so this first one, we're just going to work our way through, and I've got a total of 3 example problems that we are going to look at together. Alright, just have my notes off to the side here, make sure I'm doing what I am supposed to do. All right, here we go. All right, so we've got a penny that is made of pure copper, so it has to be before 1982. And it falls from your pocket into the cold snow. And the question is, what is the heat transfer? And then you somehow know the following because you're awesome. Your penny is about, in your pocket, so we're going to say it's close to room temperature or body temperature, which is going to be 37 degrees Celsius. The snow is -8 degrees Celsius. The mass of the penny is 3.10 grams, and the specific heating capacity of copper is 0.385 joules per gram degree Celsius. And so, for this problem, let's see here. There we go. We're just going to list out what is given to us. So we want to find Q, which would be the amount of energy transferred via heating. And we know that the mass is 3.10 grams. C, the specific heating capacity of the copper, is 0.385 joules per gram degree Celsius. And units are important here to make sure that we're all on the right page. And then we need to know the change in temperature. And we know that the final temperature, once it reaches thermal equilibrium, the copper will be the same temperature as the snow. So it'll be at -8.0. So let me back up for a second. So change in temperature is the final temperature minus the initial temperature. So the final temperature will be -8.0 degrees Celsius minus the initial temperature, which was 37.0 degrees Celsius in here and here. And so when we subtract those two things, we end up with the temperature change is -45 degrees Celsius because it gets colder. So final minus initial. Whenever something gets colder, it's going to have a negative temperature change. And that's everything that we need to know. Because what we're going to do is we're going to plug all of that information into this equation where Q equals M times C times delta T. So here we go. So Q equals M, so the 3.10 grams times C, which was a 0.385 joules per gram degree Celsius. And again, the change in temperature, we already calculated. Some people will wait to plug all that information in here, which we'll do sometimes if we're trying to find like final temperature, initial temperature. But we can just plug this in right here because we already calculated it, -45 degrees Celsius. Multiply all those things together, but before we do that, got to check the units. Unit analysis is important. Grams cancel out grams in the specific heat capacity. Celsius cancels out Celsius, and we're left with joules, which is good because we're trying to calculate the amount of energy that's transferred or the amount of heating or cooling that's happening. So we're left with Q equals, all of those things multiplied equals -53.7. If we're using proper sig figs, that would be 0.0, because when we subtract the placeholder is the thing that stays the same. So you'd be saying, oh, 2 sig figs here, 2 sig figs in the answer. But when you're subtracting, the decimal place is the thing that actually stays the same. So this one would have 45.0. So that one would have 45.0. So 3 sig figs in the end, if you care about that sort of thing. And then joules would be our unit because that's what's left here. And there we go. That's our answer. So that's the amount of energy. That's the amount of energy transferred. Now you'll notice that this is negative. So negative tells us left the system. Right? So the system is always going to be the object or thing that we care about. In this case, it was the penny. So since the energy transfer is negative, that means that energy left the system. There we go. That's example number 1. Now let's look at example number 2. Pause as needed if you'd like to copy any of this down. And here we go. So a 32.5 gram cube of aluminum is initially at some temperature and it's put in some amount of water. And that water is at a certain amount of temperature as well. And this one is going to be a little more complicated because we're looking for the final temperature of both substances once they're at thermal equilibrium. So the aluminum is going to cool down and the water is going to heat up. There's going to be some heating that's happening, energy transfer between the system and its surroundings. And we're going to assume thermal isolation because that makes it a lot easier. No energy is transferred outside of these two objects. And then it gives us the specific heating capacity of liquid water and aluminum. So in order to conceptualize how to start this problem, the amount of energy, so we're going to have like aluminum, just looking at my notes here, aluminum and water. So the amount of energy from the aluminum that's being transferred has to equal the amount of energy that's transferred into the water. And so we would say that the Q of the aluminum has to equal Q of the H2O. But we have to have a negative sign in there because the amount of energy that's going out of the aluminum has to equal the amount of energy that's going into the water. And so the signs are just going to be opposite of those. And so whenever you have the surroundings is always going to get a negative sign, just so that way the math works out in the end. Because again, your perspective matters for this. If we were just looking at the water, we wouldn't have to worry about the negative sign. If we're just looking at the aluminum, we wouldn't have to worry about the negative sign. But if you have both of them together, negative sign is important. Okay, so then we'd have to list out the following. So we'd have to have MC delta T for the aluminum and aluminum and aluminum. So that would have to equal negative MC delta T for the water. So we know so in order to set up a problem like this, you have to know like all of the variables except for one. So we know what the mass of the aluminum is. We know the specific heating capacity of this aluminum. We don't know the temperature change of the aluminum. We know the mass of the water. We know the specific heat of the water. We do not know the change in temperature of the water. So it seems like we have two unknowns, but we can be a little bit creative here and we can substitute in final minus initials for each of the changes in temperatures, and that's how we're going to end up with only one unknown and solve the problem at the end. All right, so here's what that is going to look like. So instead of this, we could say that final minus the initial, and the final is going to be the same for everybody. The initial temperature is going to be different for the aluminum. Same thing here. So altogether, this is going to seem crazy, but this is how we're going to set it up. So the mass, well, I'll just write it out. That's the full equation. But the nice thing is that we can substitute in. We can get another parenthesis there. I need to substitute in numbers, and then I can simplify it, and then we'll just have to do a little bit of crazy algebra. Not crazy algebra, but a little bit of algebra, and then we'll make it all work out in the end. So I'll put that up there so that way we can write in our givens and unknowns. And it's never a bad idea to list out like your mass of aluminum equals C of your aluminum, and so on, and then do the same thing for your water and list all that stuff out. I would recommend doing that now, but I'm just going to start substituting in values. Alrighty, so the maths. Here we go. All right, so that was a lot, right? But now we're going to be able to do some simplifying. And we can do that like so. Now there's a lot of different ways you can do the algebra here, but I'm going to try to simplify and do it in the easiest amount of steps possible. So I just did multiplication here. I dropped the units off just because sometimes that can make life just a little bit more complicated than it needs to be. And now you could distribute these and then you'd have 4 terms to deal with, but you could also divide here, which is what I'm going to do. So I'm going to divide both sides by negative 440.15. That would go away, so I'm left with TF. Now, this number is pretty small, so it's key that you bring with enough significant figures. So that way, you know, if you just put 0.06 or 0.067, that would probably not be a significant amount of sig figs to get close to the right answer in the end. So you want to make sure that you don't round as much as possible as you do these. All right, so then we need to distribute, boink and boink. The key here is to watch your negative signs. That I've messed it up 100 different times because of negative signs, and I've seen students do the same as well. So negative here, positive there. And then we just subtract 3.06 to the other side. And then we're going to try to combine like terms. So all I'm doing is just, there's like like an unwritten 1 there. So now that's just more by 1 or less, depending upon your perspective. And then lastly, we divide. With final temperature is, drum roll, the negatives cross out, and left with 17.3 degrees Celsius with the right amount of sig figs. Whew! So then we can always check back to the beginning. So we know that the aluminum was going to cool down and the water was going to heat up. So the aluminum cooled down a lot, went from 45.8 to 17.3, but it did cool down. And then the water went from 15.4 degrees to 17.3. And that should make sense. Water is really hard to heat up and cool down because it has a really high specific heat, 4. And then metals have a really small specific heat of 0.908. It's because of their atomic structure, right? Or their molecular structure. Water has hydrogen bonds, metals, their bonds are loosey-goosey, so that makes sense. That the aluminum would change a lot and the water would not change very much. Also, their masses are different. All right, got one more. I want you to try doing this one on your own. So pause, and then I'll just put the answer up here in just a little bit. Alrighty, so here we go. I listed out all of my givens and my unknown for the problem. So got the initial temperatures, got the specific heats, got the final temperature is the same for both of them because of course they reach thermal equilibrium at the end. And then at the beginning I just did my delta T, my change in temperature calculations first, just to keep it clean when I was doing the actual calculations in the end. So I calculated my delta T's. And then to help set up the problem, I just said, you know, the amount of energy transferred from the copper goes into the surroundings of the water, and since it's being transferred out of the system or the surroundings would have the negative, like there has to be that negative sign somewhere. And usually we put it with the surroundings. So then we end up with this equation where MC delta T, this is all the information for the copper, this will be all the information for the water. And then we do some substitution. So we don't know the mass of the copper, but we know everything else. So I substituted that information in here. Then I simplified, so I multiplied these. And it's always good to check out your unit analysis. So degrees Celsius, maybe the black will show better. There we go. Degrees Celsius cancels off degrees Celsius, so then I'm left with joules per gram. Joules per gram is there. And then my degrees Celsius, grams, I'm left with joules, which you can see present there as well. Notice that I have a negative sign, like my negative doesn't go away here, but I do end up with a negative sign here because of the change in temperature being negative. The negative signs are going to kill you if you're not careful. So that's that. And then I end up with doing a little bit of division here. The negative signs cross out, so then I'm left with a positive mass in the end, which is good because you should always have a positive mass. And then I chose 3 sig figs for my answer because of the variables that were given in the problem. 3, 3, 3, 3, 3, 3. No question about it. There should be 3 sig figs in the answer. So I got 37.8 grams for copper, which, all right, there we go. Awesome. Let me know if there's any mistakes. It happens. And as always, I have to leave you on a laughy, happy joke. So here you go. I think I already read that one. What did the math book say to his doctor? I'm full of problems. I am too. Why did the crazy train get in trouble? He had locomotives. Heyo. All right. Well, thanks for listening, everybody, and have a good one. See you next time.